Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so we're very happy to have today with us one of the masters of the Markov to Gaussian connection, Jay Rosen, who will tell us about the sufficient condition for continuity of permanental processes.
Okay, thank you, and thanks for the opportunity to be here. What I'm going to discuss is a type of processes which is not very well known, called permanental processes. And I'm going to explain, first of all, what they are, and more importantly, why I think they're important, how we can use them to get very interesting results about Markov local times. And then explain how to actually get results about permanental processes. So that's the basic outline. So for the background, we take a Gaussian vector, that means n Gaussian random variables, mean 0 always, and the covariance is given in terms of some matrix, Aij, some n by n matrix. So in particular, I just remind you, this says if I'm looking at the expected value of some function, g1 up through gn, then it's given by an integral of the function against the Gaussian density, which is going to be, you take the inverse of the covariance matrix, ij, xi xj over 2, integrate over all the x's, and you divide by, I guess it's 2 pi n over 2, and then what's important for us is the determinant of a with a square root. And I'm going to write this in slightly more elegant notation as simply integral of f of x e to the minus, write this as x, a inverse x over 2, and the same okay, so that's basic, almost definition of what it means to be a Gaussian vector. I guess that is the definition. And then I'm given some numbers, lambda 1 through n, and this is a diagonal matrix. And I want to do a computation now, calculation. We look at the Gaussian squared, multiply it by the lambda j. So this is basically the moment, or the Laplace transform, or the moment generating function for the squared Gaussian squares. This can be written in that form. This is my diagonal matrix lambda. And based on what I told you over here, we can write it like this. And now you can put these two together. And in the exponent, you get e to the minus x. Then there's lambda plus a inverse x over 2. When you do the integration there, for the same reason you get we have the normalizing determinant a to the half. When you do the integration, this gives you the determinant of whatever was in the exponent now, the lambda plus a inverse to the, again, minus 1/2. Using the fact the determinants, determinant of a times determinant of b is determinant of the product, we get the following form. So the Laplace transform of the squared Gaussians is of the form, well, 1 over the square root of the identity plus lambda times a. So again, a basic fact about squares of Gaussian vectors. So here comes the new definition. This goes back to David Verre-Jones in 1997. He didn't use exactly this terminology, but he started discussing such vectors, such processes. So a permanental process with kernel gamma is defined to be a positive real-valued stochastic process. So it's real-valued. It's in fact positive, just like Gaussian squares. Gaussian squared is going to be our typical example of a permanental process. And such, so it's indexed by some arbitrary set T, but require that the finite dimensional joint distributions satisfies, well, the same sort of thing that the Gaussian satisfied. Instead of Gaussian squares, I should say. So the Laplace transform of the theta xi's takes this form. And of course, this is the matrix. ijth entry is the kernel at the point xi, xj. That's our definition. We're given some kernel on t cross t, some product function, and
You no longer assume
yes, that's the key.
There's no permanent in this definition, right?
I will explain. That's a good point. Maybe I should take the opportunity now to explain where the name comes from. So, Dave, and we'll need this later on. So Jones shows, first of all, so I can erase this now. He, in fact, defined what I'll call a beta permanental process, where the Laplace transform is of the form determinant identity plus lambda gamma to the power beta. And what he shows, actually, he instead of the minus, he had a plus, and therefore this will be a minus. Let me make this a minus. So he shows that this has an expansion. So you remember, this is a diagonal matrix with entries lambda 1 up through lambda n. And this can be written as a power series in the lambdas times what I'll call gamma beta. So I must define for any matrix, so for any n by n matrix, this is called the beta determinant. And it has the following form, which looks like the expression for a determinant. So you take, the entries will be B1. So the sum is over all permutations of 1 through n. 1 comma pi 1. B, 2 comma pi 2. Dot, dot, dot. Bn pi n. And here we have beta to the power, which is the number of cycles in the permutation. As you know, you can write a permutation. You can form it into cycles. So you start off with 1 goes to pi 1, and then you look where among the first indices, well, you have pi 1, that goes to some other pi, and you get a cycle, and number of cycles. Now, when beta is minus 1, this is exactly the determinant. When beta is plus 1, this is what had been called in the literature a permanent, plain permanent. Our case corresponds to beta equals a half. So this is where the name comes from. In particular, maybe I'll just, can I just stick something over there for later reference? What you see from this is if you want to get the moments of the product, let's say I goes from 1 to n, of the theta x sub I over 2. So you would take the derivative with respect to lambda, set them equal to 0. Well, from that expansion, you see right away that this is given by the permanent, I'll put a 1/2 here for the moment, of lambda. So I'll come back, I hope, if I have time, to use that to explain things. But this is where the terminology permanent comes from.
It's real permanent only for beta equals 1. Classical.
Classical, better word. It's a very real, but
It's closer to permanental than the terminal.
sorry.
S is closer to 1 than to -1. So it's
Oh, okay. So now just repeating what we said. If we have a Gaussian process, it should have been whoops. Yeah, there should have been a singular instead of processes. But if you have a Gaussian process, then the square is a permanental process whose kernel is given by the covariance. Okay, repeating myself. And the question is, what about more general gamma? If we have a gamma which is not necessarily positive definite, not necessarily symmetric, are there permanental processes? And what, more importantly, why should we be interested in the continuity of such processes? So in the paper of Vere-Jones, he gives various criteria on a matrix or an n by n matrix that would allow you to get a permanental vector. His criteria is very hard to work with. However, we'll see in the context that I'm going to develop that there's wealth of permanental processes, and I will explain why I'm interested in continuity for them. So now I have to give some background. Let xt be a symmetric Markov process in S in some state space. You could think of it as the real line, but more generally, some nice space S. And I'm assuming that it has symmetric transition density, symmetric for the moment. Soon we'll get to the case where it's not necessarily symmetric. And transition densities means precisely that if you want to calculate the expected value starting at x for some function of the process at t, you get it by integrating the density. Well, you're starting at x, integrating the density at y against f of y.
And this dy, is it some general measure? Or is
Oh, yes. There's some general measure on S. It's, we call it the reference measure. So I should have written m of y. I think in the paper I have it right. But okay, now here's the basic fact. For symmetric densities, this is used to be the most important part of the talk, but now we've gotten beyond symmetric. But I want to show that PTXY for symmetric Markov processes is positive definite. So we study, this is what you have to look at, the double sum. We have a sequence of points, xi through xn, x1 through xn. And now we use the fact this is the transition density of a Markov process, so it satisfies the Chapman-Kolmogorov equation. So I just break T into two pieces, and I write it like this. And now use the fact that it's symmetric to change the order here from xj to move it, to exchange it with z. And then you see I get a perfect square that I'm integrating. So we have it's positive definite. And next step is we define the potential. This is also standard notation for Markov theory. You integrate in T. So once again, inheriting from the fact that the transition density is symmetric and positive definite, U itself is symmetric and positive definite. Therefore, there exists a Gaussian process whose covariance is U of xy. That's a basic fact about Gaussian processes, any positive definite symmetric matrix. And we have terminology that the Gaussian process with such with such a covariance, mean zero, always exists, and we call it the associated Gaussian process, associated to the Markov process. Okay, now we come to the connection between why it's associated. I've only told you in terms of the covariance. This is local time for our general Markov process x. What this means, f sub epsilon of x, you should think of as an approximate delta function at x. So it's a function which is peaked very highly around x. As epsilon gets larger and larger, it gives more and more of its weight to x, but its total integral of f as usual is 1. with respect to the reference measure. And we define the local time to be this limit, which we can show exists under very general conditions. If the potentials are continuous, for example, this will exist. And intuitively, and this is why it's called local time, this is measuring the amount of time that the process spends at x up till time t. Now remember, this is a continuous time process and it's a continuous space, so generally speaking, it's not really spending any time, it's just passing through back and forth. There's no, if you were to look at the Lebesgue measure, for example, of the set of times where it's actually, where x sub r actually equals little x, it's going to be 0. But nevertheless, this is a good definition. For those of you who've studied, yeah.
By the,
I'm sorry?
By the area of this?
The definition of an approximate delta function means its total integral is 1, so that gives you the right thing. There's a slight, if you're into these things, there's a different definition for semi-martingale local time, which agrees, as this does, for Brownian motion. And there, I think it's off by a factor of 2 or something. But this gives you the usual, for example, Brownian local time. And those of you familiar with Brownian motion will certainly know a lot about Brownian local time. And one of the things, at the time was considered an amazing result, was, I can't remember how far this goes back, maybe the 60s, to Trotter, showed that for Brownian motion, Lxt is jointly continuous in x and t, which is interesting because it's a rather singularly defined function in x. So the fact that it's continuous in x in particular is not at all obvious. After that, many people got involved in trying to generalize this to other Markov processes. There are results due to Blumenthal and Gautour in their book on Markov processes. There's a paper that went further by Gautour and Keston. There's later work on Levy processes, a special type of Markov processes, by Barlow and Hawkes. They really completely solved the problem for Levy processes. And this is the theorem that is the background for what I'm going to talk about here. This is the result of Michael Marcus and I. And we showed the following, that for a quite general Markov process, but symmetric, the local time will be jointly continuous if and only if the associated Gaussian process is continuous. Now, at first glance, if you're not into these things, your first reaction is, well, okay, you had one extremely difficult problem. How do you know if something's continuous? And you replaced it with another abstract, difficult problem. How do you tell if a Gaussian process is continuous? However, the point is that Gaussian processes are, well, I erased that, but the Gaussian vector is very is very special. There's a lot that one can do with it, and it turns out it was not easy, but there is a complete understanding, which I'll explain, I'll give you in a minute, of when a Gaussian process is continuous. So let me go through that.
The process is defined with respect to a reference measure?
No. The Gaussian process, all you need is the covariance. And the covariance, though, for the associated covariance is, yes, that the u, x, y, the potential, yes, is defined with respect to a reference measure. So maybe that's what you meant. I don't know.
Stationary measure for the Markov process.
To look at the
Okay. The Gaussian is not. All you need is.
back to what the
Oh, sure.
Yes, thank you.
Yeah. There it is. So u is the potential. And the potential does depend upon, these are densities, so it depends upon what measure you take. You can change that. And the Gaussian process is simply the one and only mean zero Gaussian process that has this as its covariance.
So I guess what my question is if if that's its covariance, and that covariance depends on the reference measure, then where does the reference measure enter into the local time? Or it
The
doesn't?
local, yes, it does. It enters because
This dr.
of the normalization, yeah.
Did you,
Here,
did you want to say that local time is a version of the density of the occupation measure?
that's a good way to put it. But I'm looking. Where's my slide where I define? Over here, yeah. So this approximate delta function is a function whose total integral with respect to the reference measure is 1. So you change the reference measure, you double the reference measure. This has to be halved, or double. Yeah, halved. Okay. Okay, but that's another way to put it, which I didn't plan to get into that. But if you have your Markov process and you look at yes. Yeah, so take any f of x.
You want to write higher on.
Oh. Okay, so the occupation time formula says that for any function, this can be written as f of x lxt, and this will be dx, but depending on the reference measure. So in that sense, it's a...
Allow me to interject one sentence.
Please, by all means.
So given any Markov process, you can define a measure, which is the occupation measure, which for any set measures how much time you spend in that set. Now, that measure, in some cases, is absolutely continuous with respect to your reference measure. Then you can look at the density. And the local time is a version of that density. The problem with defining the density is only defined almost everywhere. So you want to make a definition of a kind of density by differentiation, which will be defined everywhere, and then you have a chance to prove its continuity.
Thank you. Okay, so as I said, this theorem goes back, I don't know, when did we do that? Somewhere in the 90s. It's not so new. But this is the background for what I'm really interested in. Let me just flash ahead for a moment. I'll come back to this. Let me explain what's known of the continuity of Gaussian processes. This is a result, goes back to many people, but the final nail was done by Talleyrand, nail in the coffin, who showed that Gaussian process is continuous almost surely if and only if you can find a measure on the state space, probability measure, such that something holds. It's a little complicated. This is mu is called the majorizing measure. But the point is that this criterion depends only on the covariance. So there's a metric d, a distance d, which is the L2 distance between gx and gy, which can be expressed in terms of the covariance. And so we have a criteria for continuity which only depends on the covariance. There's no randomness anymore here. All the probability, so to speak, the probability of the Gaussian part has been taken out of it. Now, in practical terms, it's not always obvious, if you give me a Gaussian process, how to find whether or not there exists a measure such that happens. And, okay, so you can say in a certain sense the problem is not solved, but at least it's been reduced to a different problem. And Yuval has been working on a special case where gotten his hands on an equivalent to Talleyrand has a more recent version of this majorizing measure condition, and one can get a hand on it sometimes. But I consider this to be a solution for, okay. So let me turn back a minute to just go again, making the connection of what happened. So go back to my I went back. I skipped. It is forward for you, but in my sequence, it was. In my sequence, it was. Okay. So remember, here, this was my approximation for the local time. We have my approximate delta function at z, integrating at r. Take the expectation. Well, you interchange. And we know this is integrated f epsilon against the density. So now when you take the limit as epsilon goes to 0, by the definition of an approximate delta function, this integral, the dy integral, just changes the y to be the z. So we have a formula for the expected value of the local time, given by that, and consequently, repeating again, consequently the infinite local time, or this is what we call the total local time, is exactly the potential. So on the most basic level, and I hope I'll have time, I'm not sure if I will, I hope I'll have time to go beyond the basic level to explain better the connection. But on the most basic level, you see here a connection between local time and the potential, which means the Gaussian process. Now this gets made, this connection is made more precise by the following theorem. This goes back to Dynkin. It's called Dynkin isomorphism theorem. It's just the top two lines. It looks a little complicated, so let me try to back down a little bit, back away. First of all, this equality is not what one usually talks about when you refer to an isomorphism theorem. You'd like to say something just depending on the local time is equal to something else just depending on the Gaussian. Here we don't, unfortunately, we don't have that. The right-hand side only depends on the Gaussian process. The left-hand side, however, involves a sum, Gaussian local time, and this causes a lot of complications when you want to apply this. However, now, so we have a local time, which is defined with respect to a Markov process. I'll explain, this is an expectation, I'll explain them more carefully. Type of expectation for the Markov. The Gaussian process is taken to be completely independent of the Markov process, and therefore of the local time. I refer to its expectation as E sub g. And by this notation, I mean for any function of the xi's. One could have, for example, a countable number of the xi's. One can even have a continuum thing. If I had a continuous process, for example, I can. But for our purposes, here's how I want to use this. By the way, this expectation is known as an H transform of the original expectation. And what you see from here, so intuitively, this measure is the expected value of a process started at x, well, started at z, and conditioned to die at x. That's the intuitive idea. You see, if you only have some function which lives up till, well, you're only interested in something, this is not a, this should be an f. But if you have a function of the process only up till time t, and if it hasn't died yet, what you do is you multiply this by, well, uyx. If you think about it, yx is a probability starting at y. At the end of time, at the end of your time, when you die, you're at x. So that's the intuition. As far as we're concerned, the only thing that's important here. I don't know if I should. Yes. Okay. So using the Markov property, if you have some function, say a function of a couple of the x's at times which are less than t. So you start at z, you go to wherever the first function is, second, then you get to your nth function, and then then you go to time t, and then you're looking at u at xt, comma x. When you write out you do your expectations with Markov property, what this is intuitively saying is that at the end of the lifetime of this process, I'm looking at a process that has, it's a transient process. The potential is finite, so it dies at some point. So this is saying you do whatever the f is telling you up till time t, and then at time t, You do whatever you want, but make sure you end up at X when you die. So that's the intuition. I don't want to get too involved. We say it's conditioned to die at X.
What is zeta here?
Okay.
The killing time.
Yes, zeta is the lifetime of the process. The first time it dies. Is that notion familiar to people? So we have a process which is doing something, and then at some point or other it disappears. So we call that the death time. For example, okay, you have think of a Brownian motion inside some finite region. You run it, and you will say as soon as it leaves the bound, when it leaves the region, we say it died. We kill it when it leaves the region. So that's an example of a Markov process which has a finite lifetime. So it's a similar thing here. Okay, so let me explain how to use this in a simple way, the way that we need for our purposes, which is, let's assume that the Gaussian process is continuous. I want to show how you can use this to show that the total local time is also a continuous function. So, of course, we'll take a countable dense set of the xi's. And for f, I'm going to take the indicator function of the event that the gxi's are locally uniformly continuous. You could write that out in epsilons and deltas if you want, but you can make that into a nice indicator function of a nice measurable set. And so if in fact that we start off with a g which is continuous, therefore this is always going to take the value 1. And then the expectation here, well, this had covariance, so it's going to get a uxx, cancels that, it's going to be 1. So with probability 1, the sum of these two things is locally uniformly continuous on my dense set. Well, the sum is continuous, but our assumption is that g is already continuous. That shows that the local time is continuous. So that's, you could say, the easy part of using the isomorphism theorem. If we know g is continuous, we get that L is continuous. Now, this only tells me that the total local time is continuous. As I said, we're after something more, that we get joint continuity in x and t. That's a different story. It's much easier. It has to do with various Markov, using various Markov.
Much harder?
What did I say?
You said much easier. Yeah. Much easier than what?
Much easier than what we just said, which was...
continuity just in it.
Yeah, all right. Okay, I don't know if it's easy. That's the best way to put it. It's using Markov techniques.
Even the additional step is easier.
Yes. It's easy. I take back the ER. Once you know the total local time is continuous, then there are standard techniques which allow you to get... now there's standard techniques which allow you to get the joint continuity. Okay, let me...
You were standard before you did it.
Right.
Standard.
Yes, that was a long time ago. Now...
What is xi in this statement?
Okay, it's probably notation. This is f of many variables, and I denote them as xi. It could be x1, x2, up through xn, for example. It could be a function. In the case that I told you about, f is an indicator function. You take a countable dense set, those are my xi's, of x's, and this would be indicator function that restricted to those points, it's locally uniformly continuous. So for any epsilon, delta. Okay, so this is still part of the background. Now we come to the new material, which is, what if the potential is not symmetric now? And you'll recall the definition, the fact that we had positive definiteness also depended upon symmetry. So when this is not symmetric, in fact, it's also not always. We have examples where it's positive definite. In general, you don't have positive definiteness. But certainly, you don't have a Gaussian process whose covariance is that, because by definition it would be symmetric. So what can be done? This is where the permanental processes will come in. So this is a recent result of Natalie Eisenbaum and Kaspi. They have an analog of Dinkin's isomorphism theorem for non-symmetric Markov processes, where the role of the Gaussian square is now replaced by a permanental process. So this is my motivation. This is why it's important. And I want to mention that they show that whenever you have a Markov process, there always is a permanental process with uxy as its kernel. As I said, in general, it's hard to come up with examples. In Vera Jones's paper, I think he only has a few 2- and 3-dimensional examples of permanental processes. But here you have a whole rich family. For any Markov process, there'll always be a permanent.
These are all half permanent.
Yes. Well, we call them permanental. Yes.
I mean, the term has been used in other places,
contexts, right.
Usually with beta equals 1. So.
Okay. But now again, you can see exactly the same reasoning as before says that if I know the permanental process is continuous in X, I then get automatically that the local time is continuous in X, and easy or easier, either way, that'll give me the joint continuity of the local time. So this is my motivation for studying permanental processes and trying to find conditions which will guarantee that it'll be continuous. Conditions that just depend on the kernel. And sure enough, this is, okay, this I'm just repeating. The local time is continuous if the associated permanental process is continuous, but we don't know at this stage if it's an only if. I didn't explain to you how one goes backwards from the Dinkins thing. I didn't explain how to go backwards to show that if the Gaussian process is not continuous, the local time is not continuous. That's already a non-trivial, well, they're all non-trivial, but that's a much more delicate problem. Just as the criteria for non-continuity of Gaussian processes was a much more difficult problem in the theory of Gaussian processes. So all these things are open. And we're just dealing now with finding criteria for a permanental process to be continuous. And here's our main result, and it should look...
The Gaussian case? Yeah, how do you go? Can you just give in a nutshell how to go back?
No.
It doesn't
No, it's a different talk. If you want to come to me a little later, I can probably reconstruct it, but it's also in my book. But okay, but the point here is that the criteria we have, so we have a kernel. This is just some sort of boundedness condition, which is really not okay. But this condition is the same sort of condition for majorizing measures which give the continuity of the Gaussian process. So the first result is if you have such a majorizing measure condition, then you get a result on the permanentals. Ah, good. I'm glad someone asked that question. I'll come to that in a minute. No, it's not the same metric. But it can't possibly be the same metric. But that's a very important question. I'll come back very shortly. Let me just mention that beyond getting this result, I'm not using the word continuity yet, there's also a modulus of continuity result that, J was this, I didn't want to write it all out, this integral, this soup here, that's what we call J of delta. So in the next thing, if this J of delta doesn't decrease, yes, if it doesn't go to 0 too quickly, then we get a following result. I'll come back to this in a moment, but I want to now address the problem that you mentioned, the issue, the question, that's very important here. Whoops. Okay. So for the Gaussian case, my gamma, the covariance, the metric was the L2 metric, and you can write it like this. Gamma xx, gamma yy minus twice gamma of xy. The d that we use, forget the constant here, that's unimportant, but it's gamma xx, gamma yy minus not gamma xy. I need both of them in there because now it's not symmetric. This is what I need. Now, first, just from the definitions of a permanental process, one can show, for example, that this product is positive. So I could take a square root. Gamma xy needn't be, the individual gamma xy's needn't be positive, but the product is. Similarly, one can show that the thing inside the second square root is also always positive. So the thing is well defined. That's not important. But what's interesting, I think, is that it doesn't seem to be a metric, the dxy.
You have examples where it's not.
No. No. A lot of effort does not yield either an example or a counterexample. Nevertheless, so at this stage we're considering that it's not a metric. Nevertheless, you can still define what we're going to call balls.
Not necessarily. You have to look up the official definition of not necessarily.
Okay. Okay. We can still define what we mean by a ball, call it a ball, even though it may not have the same shape. Okay, it is symmetric. The D is obviously symmetric. And so, whoops. Yeah. So this can be defined. And
these balls as basis for open sets define the same topology as.
yeah, so the last thing was that this does give you, these balls will give you the same topology, or really the open one, you strictly less than you, will give you the same topology as the L2 topology of the permanental process. So in that sense, there's a connection with the Gaussian distance. But and therefore, to go back, we could say from this that we get continuity in the L2 metric. And similarly, the modulus of continuity can all be determined with respect to the L2 metric. But for reasons which I'll explain now, this D is the natural object to look at. So let me explain that, where it comes from. Okay. So here's the important fact. Oh, let me go. I guess you saw it already. But the question is, how do you get Gaussian process? We know so much about Gaussian processes. And just from the definition, it has all sorts of nice inequalities, etc. How are we going to get something like this of a permanental process where we know almost nothing about it? So the one thing that I consider this the key fact is that the bivariate distributions are not normal, but are the squares. So for any pair, theta x comma theta y will have the same law as a particular mean zero Gaussian vector, squares, whose covariance is given by that.
Is this an ordered pair or ordered?
They're ordered. Why? What difference?
You did.
Yes,
you don't
they're
have
ordered. They're ordered. Now, it's definitely not true that that this is the square of that the process per se is that there exists. We're not claiming, and it's definitely not true that the permanental process is the process of squares of some Gaussian process on the whole space. It's only the bivariates. Now, if you ask me, maybe the trivariate, I don't know. We can't get anything else.
It's a different.
What? Yes, for every xy, yes, it's going to be different. They won't be connected. I mean, you can have xy and xz, and then the x's well, you could see it's there'll be different vectors. There's no joint nice representation.
So this keep that holds only for the beta equals half, or is there an equivalent to?
No, it's only beta. It's half. I'll explain in a minute where it comes from. But just a background for those, not background, a preliminary to what's coming ahead. The reason this is useful is that when you see how the results are gotten by from Gaussian processes, you look at, for the continuity condition, you look at the difference of two Gaussians. It's only pairs that come in. So once I have something like this, it's likely, even though these are the squares, these are not G, but it's likely that Gaussian methods will work to give continuity. So if I have time, I will explain more. But now I want to come back to your question. How do you see something like this, and why is it only 1/2? Okay, so let's look at the Laplace transform for a pair. So the kernel, I want to write it down. Oh, you're not going to see it? Write it over here. You can see this. So the gamma for a pair is going to be the following form. You have 1 plus alpha I gamma xx. Alpha 1 gamma xy. Alpha 2 gamma yx. And 1 plus alpha 2 gamma yy. So you do the determinant, and you get exactly that form here. So I want to produce another kernel, which gives me exactly the same thing. And that's, as you could see, change gamma to be, instead of xy and yx, you have now the square root of xy, yx. And you could see, if you replace this one by the square root and that one, you'll get exactly the same thing. So that shows, by the Laplace uniqueness of Laplace transforms, that we have that property. Okay, now, to explain how the chaining argument is applied here, I just want to introduce the notion of an Orwich space norms. And the one we're interested in is x squared. And this is a definition. You want to find some constant if you divide by this. So I'm taking the expectation basically of the random variable squared. And if I could divide it by a large enough c to get it less than 1, that gives me the norm. This is Taylor. What? Ex squared. So this is tailor-made for Gaussian process. A Gaussian process, the expected value of gx squared itself might not be integrable, but if you divide by enough of a constant.
Expected value, but you mean exponential.
Yes, I'm sorry. Expected value of ex of g squared. E?
Expected value of e to the, okay.
Yeah, okay. So let's say for standard normal, make it a g squared. A standard normal, this is infinite. But if you divide by enough, 4 or something like that, it'll be finite. So this is tailor-made for Gaussian processes. And the methods of proving the continuity and modular continuity, etc., for Gaussian processes depends upon this norm. It's a crucial ingredient. And the point is that Gaussian squareds and the permanental, even pairs of permanentals, are the same as pairs of g squareds. They don't have a finite Orwich norm. So this is the hurdle we have to get around. Even though we're very close to Gaussian processes, we have to worry about this. Okay, so I mentioned that for a normal random variable, you get a. So this is the long slide, but this is the key thing. We form a cutoff version of the g squared. You cut it off at lambda and divide. Now, this is a difference of two squares, so of course, a squared minus b squared is the product of the sum and the difference. The sum, because I've cut it off at lambda half, divided by 1 over that disappears. And then, just simple inequalities show that you can bound what's left by the difference of two normals. That's perfect. That's what I want. So this object, I'm going to bound by a difference of two normals, and everything's going to work. So I call the Euler's norm of the Euler's norm of this object, my cutoff difference, I call that rho sub lambda, and it's bounded by the Euler's norm of this, which is, by the previous slide, previous slide tells me it's a constant times the L2 norm. So the L2 norm of my g, of my pair, is what I call dxy. The constant was, okay. Now, so I want to just show that the sup has finite expectation. So the chaining argument tells me that for any lambda, I get the following, that my cutoff object, which is bounded by the difference of the Gaussians, the Gaussian techniques, tell me that this is bounded by, if you remember what J was the majorizing measure integral. And since rho lambda is bounded by d, I get a bound which is universal. Now z is some random variable which has nice moments. That's all we need here. So this is, again, can't give you the proof, but this is a standard called chaining result. And now what we want to do is transform this. So this is for each fixed lambda. I want to transform this to actually show the permanental process itself has finite. The sup has finite expectation. So here we use, first step is you multiply by the denominator throughout, move this to one side. This is some fixed x0. And now we use a trick which goes back to Martin Barlow, which he used in his work on Levy processes. He had a similar situation. So we define the set where it's greater than lambda. And notice the following. If we're in a... Too many omegas there. It should have been... okay. But if omega is such that sup is greater than lambda, then from what we just had... Remember the sup was less than that. So if for those omegas for which the sup is greater, then this sum is greater than...
So A lambda is actually the omega such that this happens, right?
Yeah, it shouldn't have been. This omega should have been deleted. A sub lambda is a set of omegas such that. And now a simple algebra, maybe not so simple, but after a few minutes you could figure this out. If you have an inequality like that, you can bound it by that. Which means there's no more lambda here anymore. Okay, now, if you ask me what's the probability that the sup is greater than lambda means of this set, well, it has to be, on this set we have this inequality, so either this is bigger than half of lambda, or that's bigger than half of lambda. And from this, so this is a single permanental. As I said, it's marginal. A single permanental is a Gaussian squared, so it has a finite expectation. You integrate these with respect to lambda, d lambda. And I also said that these have it's a random variable that has nice moments. And so we established that the sup is finite. That's the main way we get around the fact that we're dealing with theta x's which are related not to Gaussian but to Gaussian squares. You can't directly use the Gaussian results. You have to use some sort of cutoff version. And finally, the same thing tells me that by a chaining argument, we get the same situation now for if I'm looking where the distance in the metric is less than delta. We get some result like that. But there's a lambda out there, lambda 1/2. And so we pick lambda so that it's between close to the soup. And therefore, I get this result. So notice, in Gaussian processes, you simply show, you don't have this in there. You show that if you have a difference between two Gaussians, you look at the soup over some small interval, is bounded in terms of this metric entropy integral. But this is not an artifact here because the analog for us would be g squared. And you'd look, the difference between two squareds is the product of the difference, which is bounded by the z and the metric entropy, times the sum of the g's. So for the sum of the g's, I have to bound it by this. The square root of the square is giving me the soup. So this is the right sort of result that we expect.
Thetas don't have to be positive?
Thetas are positive. Thetas are positive.
Couldn't you try and look at modulus continuous square root of theta? Try to show that has the Gaussian.
Well, think about it. If we had g squares and the square root of them, it's no longer a Gaussian. They're the absolute value of Gaussians. And we don't have a whole process. So it would be nice to see that, but I don't know how to do that further. Okay, so if I run out of time, I'll stop here. There were several other things I could do, but I'll leave it up to you.
You have 4 more minutes.
4 minutes. Okay. But I'll be glad to talk to anyone else more deep. There are 2 interesting things that I don't have time for. One, maybe in 4 minutes, I can give a little exposition of one of them. The one thing I won't talk about, but which is not, the general idea is not so hard. We're on the verge of it, but is explaining how the basis of the isomorphism theorem. We're close, but it needs maybe 20 minutes or something, which I won't do. The other thing I could just, in 2 minutes, there's another application of this, or at least connection, with what's called loop soup local times. And I'll just mention what that is without getting into too involved. But these things recently have a lot of interest. Lejeune, recent Sanfour lectures, spoke about this, and they're available on the web, the loop soups. But he dealt with symmetric Markov processes. But here's what you do. So I'm going to erase this. Okay, so we start off with some Markov process. And we define the following measure. I'll have to explain everything in it. But so mu of A. So A is some set of paths, some path space for the process. And it's the following integral, double integral. First you integrate e to the minus t over t. I guess I didn't. Then what I'll explain what pxx sub t of A on the set where the lifetime of the paths when they die equals t. And you integrate this, here I have the reference measure, dt. So it's not at all clear why this is of interest. In general, it's not a finite measure. It's a sigma finite measure. Pxxt is what we call a bridge measure. This is a measure which is built up from the original px. And essentially, it gives you a measure for paths which are conditioned to die at time t at the point x. So they start at x, they do whatever they want, or they're just about to hit x. So more precisely, x sub, if this is the process, x sub what we call t minus, the left limit is equal to little x. So these are measures that one can construct from the original process, the bridge measures. And in that sense, we can, so this is also the starting point here. So in this sense, we can think of these as a measure on loops. And this is the loops of length or time t, and you integrate over t, so you have a lot of loops out there. Now, you take this measure of loops and you make a Poisson process whose intensity measure is this mu. So what that means is, roughly speaking, you get a random variable whose value is a countable collection of loops. And you can then form what's called the loop soup local time. I'll call it L hat of x. This is going to be, you take the local time, our usual process local time at x, the total local time of a path, and you take these paths, the sum over the countable, let me call it.
No one can see anything.
Oh. Okay, do it up here. The loop soup local time is going to be essentially the sum of the local times for each path in my soup, so to speak. And so the connection is that this is a permanental process. So that's what I wanted to mention. So there's another application is to loop soups. Okay.
More questions?
Any answers?
They will be here until Thursday evening, or someone who wants to
Hear about the isomorphism
further
theorem?
isomorphism theory?